In this lesson, we are going to discuss fluid pressure and fluid force. Now, one thing we are going to be able to do after learning the topics of this lesson is determine the force exerted by a fluid on some kind of vertical wall, such as a dam or the side of a, say, gasoline tank. And finding the force exerted is pretty easy if you have a horizontal surface, but when you have a vertical surface, it's a little bit more complicated. So we start with the definition of fluid pressure. Now the pressure P on an object at a depth h in a liquid is given by P equals W times H, where W is the weight density of the liquid. So for example, if we're in the traditional American system of units, that would be given by as something like pounds per cubic foot, for example. And then the variable h would be measured in something like feet. And notice that in this particular example, that would make the units of our pressure pounds per square foot. And let's think, does that make sense? Well, when I think about pressure, it often isn't in terms of fluids, but in terms of pressure on my bike tires. So the units for that are PSI, or pounds per square inch. So same kind of idea here, it's just pounds per foot squared. A principle that we will be using to start this process is something called Pascal's principle. And this says that a pressure exerted by a fluid at a specific depth is the same in all directions. So let's write that down. The pressure exerted by a fluid at a depth h is the same in all directions. And that is assuming that your depth is the same. So if you have, say, a point that's at a specific depth 8, the pressure on the top is the same as on the sides and on the bottom. Okay. Also note that pressure is a force per unit area. So P equals F over A. Think pounds, which is a force, for example, per square inch, like with cars and bikes, force per unit area. And we can take this equation and we can solve it for the force. So force is equal to pressure times area. And from above, we know that pressure is weight density times height. So force is weight density times, well, height, they mean depth, times the area. So here's the thing for fluid force, or the force exerted by a fluid, we have F equals WHA, where W is the weight density, H is the depth, A is the area. And notice that this force, at least in the American system, will have units pounds. In the metric system, it will have units newtons. Okay, so consider a really simple example. Suppose we have a piece of sheet metal and its area is 5 square feet, and the sheet is submerged horizontally in 10 feet of water. So think line on the bottom of a pool or a lake or something that's 10 feet deep. So try to draw 3D. So there's that sheet that's flat. Its area is 5 square feet. It's at a depth of 10 feet. And from above, we know that force is equal to pressure times area, and pressure is weight density times depth times area. And we're going to assume that the weight density of water is 62.4. That will be different for different things, so for it actually even depends on the temperature, so we're grossly oversimplifying here, but I guess we do that a little bit in math. So we have 62.4, depth of 10, and an area 5. And we could be good physicists and put our units in there. We'd have 62.4, that would have units pounds per cubic foot. 10 would be measured in feet, and 5 would be measured in feet squared, and you can check and see, is it a units of force that comes out in the end, and the answer is yeah. The feet's all cancel, leaving just the pounds, which is a unit of force. So this force exerted by this fluid is 3,120 pounds. So it's easy to calculate the force if you have something lying horizontally. But what if instead this plate was vertical? So like this, and let's just assume that this was 10 feet. Now here the issue is you no longer have a constant depth, so that variable is changing. The depth here is different than the depth there, so the force exerted at the bottom will be greater than the force exerted at the top because the depth is greater. And so to find the force on an object like this, we're going to have to use calculus by dividing this thing up into chunks, finding the force on a chunk, and then adding all the forces together. All right, here is the equation we're going to use. So the force F exerted by a fluid of constant weight density W per unit of volume against a submerged vertical plane region from C to D is given by the weight density times the integral from C to D, h of y, which is the depth, and it's going to be a function, and L of y is the horizontal length. And I think it's important to sort of discuss why this is true. So let's draw a picture, and we have some sort of plate, give it some sort of weird trapezoidal shape, submerged in water. And let's say its base is at a y of C and its top is at a y of D. Now, like we said before, to compute the force for a small slice, that will be the pressure on that slice times the area of that slice. And the idea is you have to go in little slices because to compute the pressure, you have to factor in the depth, and the depth will be changing. But if you cut small enough chunks, the depth is approximately constant on that chunk. So pressure will be given by W times H of I, A sub I. And so if this little rectangle has height delta y, this distance from end to end is what I'm going to call L of y, or the length of y. And that'll be different for different slices, so we'll say L of y sub I. So W H sub I, L of y sub I times delta y. And that H equation will also be a function of y, as it's going to be changing. So let's write that as W H of y sub I, L of y sub I, delta y. So that's why the equation is what it is. This is the force on one small slice. To get all the slices, you add them up. So the total force is equal to a limit as n goes to infinity of a sum of all these forces, I equals 1 to n, which then makes an integral from whatever your C is, whatever your D is, W H of y, L of y, dy. And that W is a constant, so it can factor out. Let's start with a pretty simple vertical plate. So find the fluid force on a vertical plate shaped in the shape of a square with sides of length 4. that is submerged 2 meters underwater. So draw a picture. I suggest putting the water level at the x-axis. So sides of length 4, and let's just center it. So down 2, and goes out 2 in the x direction, back 2 in the y direction. 1, 2, 3, 4, down 2, -6. So there is my plate. Now the general way we're going to find the force is W integral C to D, depth times length of a slice, dy being the little thickness of the slice. So the nice thing about this one is that if you cut your little plate into chunks, the length of each slice is the same. So in this case, we have L of y is equal to 4. Now we need to find h of y. Remember, that's your depth. And before we do that, I think it probably is best to talk about what the bounds on that integral are going to be. And also we can plug in 9,800 newtons per meter cubed for that W. Okay, now our integral will start at -6 and end at -2. Those are the y values that we have. So notice that that bottom point corresponds to a depth of 6, like meaning how deep down. This point corresponds to a depth of 5. So to have an equation that describes the depth, you need to make it -y. Then when you plug in y equals -6, you get the depth is 6. When you plug in y equals -5, you get the depth is 5. So that's your depth equation. And the fact that it's 2 feet down is accounted for in the fact that the bounds of the integral are -6 and -2. Had that thing been not all the way submerged, those bounds would have been -4 and 0. So plug in -y. That would have units meters, just to keep track. L of y, that's 4, also meters dy. When we integrate, we're going to make this into meters cubed. So that's 9,800. Now in the integral we have, so you got the integral of -4y dy from -6 to -2. So that's -39,200 over 2y squared, evaluated from -6 to -2, or -19,600 times 4 minus 36, or 627,200. And let's think what the units would be here. Well, that coefficient was units Newton per cubic meter. The integral would be cubic meters, so this is going to be back into newtons. Next, let's consider an example where the length of the sides of the tank changes as you approach the bottom. So we have a tank that has whose sides have the shape of an isosceles trapezoid that is 4 feet across the top and 2 feet across the bottom, and the height is 3 feet. We're going to assume that this tank is full of water. What is the fluid force on the vertical side of the tank? And we're going to use the fact that the weight density of the water is 62.4 pounds per cubic foot. All right, so first let's draw a picture. So isosceles trapezoid, 4 feet across the top. So 2 on this side, 2 on that side. And depth of, or height of 3 feet. So 1, 2, 3. And 2 feet across the bottom. So I have a corner here and a corner here. This is approximately what an isosceles trapezoid looks like. There you go. Okay. So we know that the force is equal to W integral C to D, H of Y, L of Y, dy, and let's just fill in what our bounds are. So our deepest point is a y value of -3 up to 0, H of Y, L of Y, dy. Okay, so H of Y in this case is very similar to before. H of Y is still -y. Now to find L of Y, first notice that that is the length of a slice, say, visually. And from here over, the part I just colored in, that is x, the horizontal distance. So if I can get an equation of this line, and I solve it for x, L of y will be twice whatever x is. And thankfully this is actually pretty easy. There's a little bit of geometry going on here. So look at this purple line. The slope of that purple line from this point to this point is 3. You rise 3, you run 1. So m equals 3. And you also see that it goes through this point. Well, that point is the point 2, 0. So to find the equation of the line, you plug into point slope form. That's not the only way, there's another way, but that's the way that I prefer. And you'll have y minus 0 equals 3x minus 2, or y equals 3x minus 6. Now we just need this equation with x isolated. So y plus 6 equals 3x, and therefore x will equal 1/3 y plus 2. And just note that that only tells us the distance from the y-axis over. So to get the total distance, we have to multiply that equation by 2, and we get 2/3 y plus 4. So this will let you take any given y value and figure out what the depth is. So for example, test -3. At -3, you know that the width is 2. When you input -3, you get -2 plus 4, which gives us 2. At the top, you know the width is 0. When you input 0, you get 2/3 times 0 plus 4, which is 4, and that's the width. I mean, it's not as if something, if it works for 2 points, it works for all the points, but at least gives you an idea that this probably is plausible. All right, so let's plug those things in and go. So weight density, 62.4. The integral still goes from -3 to 0. H of y is still -y, and L of y is 2/3 y plus 4. I'm going to take that negative out and distribute the y. So 2/3 y squared plus 4y dy. Now let's anti-differentiate. So that will be 2/9 y to the third plus 2y squared, evaluated from 0 to -3. Or -62.4. When we plug in 0, we get out 0, minus. Now when you plug in -3, we'll have 2/9 times -27 plus 2 times 9. So that's -62.4. All right, 27 divided by 9 is 3. Multiplying by 2, we have a 6, and just keep track of your negative signs. So -6 plus 18. So that's -62.4 multiplied by -12, which gives us finally 748.8. And since we're talking about feet, and we used pounds per square foot. This will have units pounds. So next, suppose we have a different shape. Suppose we have a circle. So we have a circular observation window on a ship, and it's in the ocean, and it has a radius of 1 foot, and the center of the window is 10 feet below the surface. What is the fluid force on this window? So there are lots of ways to set these problems up. With circles, it is easiest to center them at the origin, and that is also a reason that they gave the depth in terms of how the center was relative to the top of the water. So if we draw a circle of radius 1 at the origin, 1, 1, 1, 1, there's our approximate circle. Its equation is x squared plus y squared equals 1. And the center is 10 feet down. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so there's the water. Now we need to find the length of a random slice and the depth. So let's write down what our integral is. So we have the force is the weight density, integral from C to D, h of y, the depth equation, times the length of a slice, dy. Okay, so first let's find h of y. So we want to know how far down from there to a random y value. Well, it looks like this distance is y, and the total distance is 10, so the depth should be 10 minus y. And I always have to convince myself that this is true by plugging some numbers in. So suppose, for example, we were at this y value of -1, which corresponds to a depth of 11. Notice that when you input -1, this depth does come out to be 11. When we are at a y of 0, our depth is 10. That's still true. When we're at a y value of 1, the depth is 9. So this appears to be okay. Now, the length of a slice will once again be 2x. So once I solve my equation for x, it'll be twice that. So getting x by itself, we have x squared equals 1 minus y squared, or technically x equals plus or minus the square root 1 minus y squared. The positive part actually gets this half of the circle, and the negative part gets this half of the circle. But in any case, one of them measures that distance. So to get the total distance from side to side, you must multiply by 2. So we have that L of y is 2 times the square root of 1 minus y squared. All right, now let's fill everything in. So the total force will be 64 pounds per cubic foot. The integral goes from -1 to 1. Our h of y is 10 minus y times 2 square roots of 1 minus y squared dy. And I'm just going to take that 2 out as a coefficient and make this into 128. And I'm going to do 2 other things at the same time. I'm going to distribute this 1 minus y squared to the 10 and the y. So I have 10 root 1 minus y squared dy minus the integral from -1 to 1 of y square root 1 minus y squared dy. And this integral involves 2 clever things. So here is the first clever thing. This particular integral, this is an odd function on a symmetric interval. So pictorially what that would look like is you have something like this, and you're finding the signed area under that curve. Notice that the positive area will cancel with the negative area, giving you 0. So that integral is 0. If you didn't see that and you try a u sub will work, it's just that you're going to get that the integral is 0 in the end as well. So if you feel as if you're uncertain and don't believe me, you could try to let u equal 1 minus y squared, and you will find that that integral is 0 as long as you make no arithmetic mistakes. So that just leaves us the second one. So we now just have 1,280, because I factored out my 10, integral negative 1 to 1, root 1 minus y squared dy. Now technically here you could use a trig sub, but you don't have to. So the fact that this is y or x doesn't really matter. If it were x's, and you could just change the variables to x's by letting y equal x, that picture is going to be a semicircle of radius 1. You did stuff like this back in calculus 1. So the area of a semicircle is going to be 1/2 pi r squared. So we have 1,280 times 1/2 times pi times 1 squared. So that's 640 pi pounds. Don't get freaked out by the fact that the variable there is a y. The bounds tell you it's a semicircle. And whenever you see root 1 minus y squared or root 4 minus y squared, root 10 minus y squared, you're going to have to think, okay, that is some kind of semicircle of some specific radius. So here's the final example, something that isn't water. So you have a cylindrical gasoline tank, and it's placed so that the axis of the cylinder is horizontal. So it's sitting sort of like a fuel tank would. Find the fluid force on a circular end of the tank if the tank is half full or completely full, assuming that the diameter is 4 feet and that gasoline weighs 42 pounds per square foot. So since the diameter is 4 feet, we have a circle of radius 2. So let's center that at the origin, over 2, up 2, left 2, down 2. And the equation of a circle of radius 2 will be x squared plus y squared equals 4. Remember that the force will be W integral c to d, h of y, depth, times the length, dy. Okay, so if we take this thing and we have a slice, once again, the length will be twice that equation solved for x. So x squared equals 4 minus y squared, and x equals plus or minus the square root 4 minus y squared. My L of y function will be twice the root 4 minus y squared. Now the depth equation. So this distance is 2, and if we have some other random, like suppose we had this point right there, that distance is y, the distance from top to that slice is 2. So once again, I think it's 2 minus y. Let's just confirm by plugging some numbers in that works for the lower points as well. So when you plug in, say, -2, you'll have 2 minus -2, or 4, which is what the depth would be. So there is your depth function. And the weight density here is 42. So we have 42, an integral, and if we're only half full, our integral only extends from -2 to 0. That's one difference with this problem compared to the previous one. H of y is 2 minus y. L of y is 2 times the root 4 minus y squared. We proceed more or less the same way as a previous example. We take out the 2 and distribute the root 4 minus y squared and break up the integral into 2 pieces. So first, this 2 can factor out, making 84. And we'll have 2 roots of 4 minus y squared dy minus the integral from -2 to 0 y root 4 minus y squared dy. Now this first bit here, once we factor the 2 out of it, so twice the integral from -2 to 0 root 4 minus y squared dy. So once again, it is still a circle of radius 2, but the fact that the bounds go from -2 to 0 means you only have that part of it. So it's a quarter circle, 1/4 pi r squared. So 84, 2 times 1/4 pi, and the radius is 2 squared. So that looks like that's just going to be 2 pi. Okay, now this other piece, we're going to have to use a substitution on it because we no longer have a symmetric interval, so we can no longer conclude that that integral is 0. So the substitution we'll make will be u equals 4 minus y squared, and du will be -2y dy. So -half du equals y dy. And let's change our bounds. If y equals -2, u will equal 0. And if y equals 0, u will equal 4. So plus a half, because the negatives cancel, integral from 0 to 4, u to the 1/2 du. So 1/2 times 2/3, u to the 3/2 from 0 to 4, plus, so that's going to be 1/3 times, so 4 to the 3/2 is 2 to the 3rd, or 8. So distributing, we have 168 pi plus 84 times 8 over 3. And believe it or not, 3 actually goes into 84 evenly, 28 times. So 28 times 8 will be 244. So your final answer is 168 pi plus 224 pounds. Now part B asks us to figure out what would happen, what the force would be if the tank was completely full. So you've done most of the work. The setup is the exact same, except for the bounds, instead of being from -2 to 0, they're going to be from -2 to 2. So let's set that integral up. So for part B, the force will equal 42 integral -2 to 2 minus y times 2 square root 4 minus y squared dy, or 84 integral -2 to 2 square root 4 minus y squared dy, minus the integral from -2 to 2 y root 4 minus y squared dy. So now we have a symmetric interval here. So we can conclude that, and because this function is odd, we can conclude that that integral is a big fat 0. Okay, this one we will have 168 times the integral from -2 to 2 of square root 4 minus y squared dy. And you still have to revert back to your semicircle picture. But this time, because the bounds go from -2 to 2, you don't have a quarter circle, you have a half of a circle. So we'll have 168 times a half pi times 2 squared, which is 168 times 2 pi, or 336 pi pounds.